All right, I think that we can slowly start. The people hopefully might come.
Yeah, I'll try
as the session
sharing.
goes. Sure. So Emily, I give floor to you.
So can you, oh God. Can you see that, everyone?
Mm-hmm. You can see it.
Great. Okay, I'll start then if that's all right.
Please
so this is some joint work with David Harvey and Steve Laybourne. And what we're doing in this paper is proposing a real-time monitoring procedure that can detect both the emergence of an asset price bubble and also the subsequent crash of that bubble as well. So recent events like the global financial crisis, which was of course closely linked to bubbles in housing markets, have highlighted how detrimental asset price bubbles can be, not just to the market where they're contained, but to the whole sort of financial system. And in 2013, Ben Bernanke gave a series of speeches where he said that it's unavoidable that there will be bubbles in the financial system, and therefore it's crucial that their emergence is taken seriously. Well, in order to do that, we need to know when bubbles exist. And so this has kind of emphasized the need for econometric techniques, which can help us detect those bubbles. And much of this resurgence in the econometric literature has focused on the rational bubble literature, because that tells us that we can model asset bubbles as explosive autoregressive processes. So you look at this AR1 model we've got here. If that parameter phi is greater than 1, we have an explosive autoregression. So a lot of the recent work in explosive bubble episodes from an econometric perspective has focused on historical detection. So being able to ask, well, was there a bubble in house prices? Was there a bubble in stock markets or oil or whatever else? And whilst this is interesting, I think that for policymakers, perhaps a more relevant question is there a bubble going on now? So being able to detect these sort of ongoing bubble episodes. And in a 2017 paper, Astle et al. Proposed an econometric method which looks at detecting end of sample bubble episodes. But moving beyond that, perhaps not only we want to say, well, is there a bubble now? But if the answer is no, then maybe tomorrow we observe some more data and we want to say, well, what about now? And the day after, maybe we get some more data and we want to say, what about now? So we want this sort of real-time monitoring approach where every time we get new data, we can ask the same question and we can monitor, are we currently in a bubble or not? Now, to do that kind of real-time monitoring approach, that implies we would need to take a test like the Astle test and apply it again and again as each new observation of data is released. But if we do that, then we're going to encounter a multiple testing problem, because now I'm giving myself lots of goes at rejecting the same null hypothesis. So the overall size of this procedure is going to be high. We expect it's going to be inflated, and it's also unknown. So this is a problem for real-time monitoring. So to kind of try and resolve that issue, in 2018, Astle et al. Propose a paper where they have a method for real-time monitoring where the false positive rate of this procedure can be determined at any point into the monitoring horizon. And I'm going to call this AHLST from now on. So we think an equally, if not more important problem to monitoring for the emergence of a bubble is then being able to monitor for that subsequent bubble collapse. Now, in the context of historical bubbles, some authors have suggested we can model a bubble crash as a stationary process. So what we're doing in this paper is we're proposing a real-time monitoring procedure that will detect both the emergence of an explosive bubble and also the stationary collapse. And we're setting this up in a way that crash detection is conditional on having first detected a bubble. In our procedure, we're coming up with a new test statistic. It's a very simple test statistic that's a function of the first differences of the price series. And we're going to implement that using modification of the AHLST real-time monitoring algorithm. This allows us to deliver a predetermined false positive rate for the bubble detection and a conservative false positive rate for our crash detection. So this is the DGP that we're using. We're imagining YT as a price series. It's equal to a constant and UT, where UT is an AR1 process. UT follows a random walk up to tau1t, where tau1 is some proportion of our sample. At which point, if delta 1 is greater than 0, we now have an explosive bubble phase that continues up to tau 2t at some later point in our sample. And then if delta 2 is less than 0, we have this stationary collapse regime. And perhaps after that, we revert back to a random walk world. So if delta 1 is greater than 0, then YT is temporarily explosive. So the first set of hypotheses that we're interested in testing between is the null that delta 1 is equal to 0 against the alternative that it's greater than 0. And if and only if we're able to reject that null, so we think that we're now in an explosive bubble, we're then going to move on and and examine a second set of hypotheses based around delta 2. Because if delta 2 is less than 0, YT undergoes a stationary collapse. So the second set of hypotheses we're interested in looks at the null that delta 2 is equal to delta 1, so basically the bubble is still ongoing, against the alternative that delta 2 is less than 0, and we now have a stationary collapse. So implicit in this, I'm assuming that a crash must follow a bubble, that a crash doesn't occur directly from a unit root regime. We're going to look at two test statistics to try and distinguish between these regimes. These test statistics are computed over subsample windows of M observations, and the idea is that we can use the same statistic for both bubble and crash detection. So the first statistic I'm interested in looking at is the one proposed by AHLST. We're calling this the A statistic. This is essentially equivalent to looking at the significance of a linear trend on a regression of the first differences of Y. And given that we know this test or this statistic works very well to detect an upwards explosive regime, it makes sense to see whether it could also help us detect a downwards collapse regime as well. And then the second statistic that we consider, this is our new statistic, which we're calling S. You can see this is a function of the first differences of Y. So if we remember, we're computing this over a window of M observations. On the numerator there, we're essentially taking the most recent change in Y and multiplying that by a sum of the previous n-1 changes. And the rationale for this is that under a unit root null hypothesis, the expected value of our S statistic will be 0. In an explosive bubble, it will be positive and getting larger in magnitude as we get further into the bubble. And as we transition from an explosive bubble to a stationary collapse, that statistic should be negative and large in magnitude. So that should help us distinguish between these regimes. We're going to implement these statistics using a modification of AHLST's real-time monitoring algorithm. So imagine that we want to start monitoring for a bubble today. We need to choose our finite window length M, and then we're going to let today minus M essentially form our initial training sample. So we're calling from t equals 1 up to t star, that's our training sample. And I'm going to compute our test statistic over rolling subsamples within that training sample. So we get a whole bunch of training sample statistics. And we're going to find the maximum statistic and the minimum statistic within that training sample, and they essentially become our critical values. So you can see I'm labeling those A star max and A star min, and equivalent for the S statistic as well. And then our first monitoring statistic is going to be computed using the data from t star plus 1 up to t star plus m today. Okay. And to make decisions about our hypotheses, we just want to compare our monitoring statistics to the critical values that we got from the training sample. So we can define our procedures as follows. If we focus on the A statistic first, you can see that for bubble detection, which I'm calling A max, we're going to reject our null hypothesis at some point in time if the monitoring statistic is bigger than the maximum we got from our training sample. If we reject at that point, then I think we're in a bubble and I want to switch into monitoring for a crash. We're calling that procedure A min, and we're going to reject that second null hypothesis at some later point in time if the monitoring statistic is now smaller than the minimum that we got from our training sample. And obviously exactly the same thing can apply to the S statistic as well. The nice thing about setting it up in this way is that for some point in time in our monitoring period, we can determine exactly what the false positive rate will be. Okay, so if you told me I want to monitor 30 periods into the future, we could set T diamond equal to 30, and we could sort of plug it into this equation, and we get an approximation then of what the false positive rate alpha would be at that point in time. Or if you were really concerned about only monitoring whilst maintaining a certain level of the false positive rate, maybe you want to restrict it to 10% or 20% or something, we could rearrange that equation. You could pick a value for the false positive rate alpha, and we could tell you how far into the future you should monitor. That handles the bubble detection. In terms of the crash detection, a nice feature about what we're doing is because we're only monitoring for a crash conditional on first finding a bubble, the false positive rate of those crash tests can never exceed whatever the false positive rate was of the bubble test at the time of the rejection. So once we think we're in a bubble, we can monitor for a crash as far as we want into the future, knowing that our false positive rate is capped at some value. Okay, so I'll just show you some results so we can see how well these procedures work in practice. I've got the same DGP setup that we had before. I'm going to use 10,000 Monte Carlo reps, and I'm setting my finite window here, M equal to 10 observations. Of course, we've tried other settings of N without any particularly interesting results. So in this simulation setting, I'm setting my training sample T star to 200 observations. Delta 1 is bigger than 0, so we do have that explosive bubble phase. Delta 2 is smaller than 0, so we do have that crash phase as well. The bubble starts at T equals 215. You should be able to see that dashed vertical line. The crash starts at T equals 225, and the crash ends at T equals 235. This solid red line is plotting the theoretical false positive rate. And at first, I'm just plotting the rejection frequencies for our A statistic, and this dashed magenta line, that's the bubble detection procedure. And you can see there the rejection frequency is tracking the theoretical false positive rate until the start of the bubble at T equals 215, at which point it begins to rise, and by the end of the bubble, that rejection frequency is around 95%. So that's working pretty well. But if you look at that solid pink line, which is the crash detection, you can see when the crash starts at T equals 225, the rejection frequency is still at 0. And even when it begins to rise above 0, it doesn't rise very much before it starts leveling off. So it looks like this statistic, although it does well to monitor the start of a bubble, it doesn't do well at all at monitoring the crash. If I add on now our S statistic instead, you can see from the dashed blue line that again, the bubble procedure looks like it's working quite well. There is a slight lag compared to the A statistic, but nothing to worry about. What's pleasing is if you look at the solid blue line, which is the crash detection, you can see that the rejection frequency is somewhat below the theoretical false positive rate, all the way until the first observation of our crash when it shoots up. So this is a nice result. It looks like we're able to get the start of the crash with some degree of power here. And just to confirm that this is working, we can look at a histogram of the detection dates by these procedures across the 10,000 Monte Carlo replications. If you look on the left-hand side, this blue line is the true bubble start date. And you can see that comparing the A and the S procedure, there's not a huge amount of difference between them. Whereas on the right-hand side, if you look at this red line, that's the true crash date. You can see with the A procedure, there is quite a bit of a lag there between the crash date and the procedure picking anything up. Whereas the S procedure seems to be getting the true crash date dead on most of the time, which is pleasing. So we would recommend using this S procedure, this S statistic, to detect both the emergence and the subsequent crash of any bubble. And then with my last few minutes, I just want to talk through an empirical application of this to some house price data. We're looking at US house price data. It's quarterly data running from 1975 to 2018. And what we've got here is this top graph is the actual data itself, the house price data. And on the bottom graph, I'm plotting the values of the test statistics. So we need to imagine that it's 1997 and we want to start monitoring for a bubble in house prices. And I pick my M, my window length of 10 observations, and everything else becomes my training sample. I'm computing those test statistics over rolling windows of 10 observations within that training sample, and I find the maximum value of the statistic and the minimum value of the statistic in that training sample. And you can see I've put on these dashed black lines to show you the value of that maximum and minimum. And now we want to start monitoring for a bubble. And remember, because we're monitoring for a bubble, we're looking for a value of our test statistic which exceeds the training sample max. So we can add this on, one observation at a time. And you see fairly quickly there, we do detect the start of a bubble. Now that we think we're in a bubble, we're going to switch into crash detection. And so now I'm going to signal that we have a crash if the value of my test statistic is smaller than the training sample min. Okay, so we can keep adding this on one observation at a time. And you can see at the moment, the test statistics are very much hovering around that maximum, while prices are getting higher and higher. And we keep going. And now we find a crash. Okay, so if we were doing this in real time, this is the point that we would say, okay, we think house prices are beginning to crash. Now, from visual inspection of the data, I don't think it's too obvious at this point that this is the beginning of the crash. But we can see what happened next, this. Okay, so this is what happens after we signal that we have a crash, and then normal market conditions resume. So we think we have something that seems to be working quite nicely here. It's not prediction in any sense, that's not what we're trying to do, but we think we have a procedure that signals the start of a bubble and signals the start of a crash before it becomes obvious just by sort of visual inspection of the data. And we recommend our S procedure as this is the one that seems to work the best. And that's all I need to say about this. I'm very happy to take any questions if there are some.
Hi, Emily, can you hear me?
I can, yes.
Hi, here's Sebastian from Munich. I have a question. Which exact date was the crash or the detection of the crash?
It's a good question because I don't have the exact date there. I think it is very late 2007 or it might be Q1 2008.
Okay. That would be interesting to see the exact date. Because recently I read an article and I saw that the housing index went down in April, around April 2006. Mm-hmm. And shortly after there was this crash. But very interesting. Thanks for the presentation.
Thank you. Yeah, I think in terms of sort of historical detection, there are better methods to use. So if we were, if our primary motive here was sort of what was the date of the house price crash, I think in that case, because it's already been observed, you'd be better off using a method for historical detection in that context, and that would give you the sort of accurate date. Whereas with this, I'm trying to sort of illustrate what would happen in a real-time monitoring context, how this would work if we hadn't already observed the data. But it is an interesting topic. There's obviously a lot of focus on housing markets at the moment.
There is a question from Adam, I think in the chat. Adam asks,
right.
has it been applied to the stock market at the advent of COVID? And I'm sorry for my
no, I haven't done that yet, but you're right, that would be a really interesting thing to do. And it's certainly something I want to do more with this at the moment, because I think at the moment most of my applications are focused on kind of macroeconomic series, and it would be really nice to see how this might work in the context of more high frequency data. So rather than looking at sort of big economic bubbles and crashes, but within the financial system, sort of looking at these almost like micro bubbles, these sort of smaller upwards and downwards movements. So yeah, it's something very interesting that I absolutely want to do.
All right. I don't see any questions more. So Emily, thank you very much for your presentation. It was extremely
That good, huh?
interesting and important. That was honest. That was honest. It's not me cutting my tongue. So as next, we have the presentation of Tiago. Tiago, I believe I should play your recording right now.
Yes, please.
Right. Let's do it. And because we are online, and as academics, we always struggle with computers during the presentations. Let me set the screen. All right. Hopefully you see the screen.
Yes, I can see.
About one of the most recurrent issues in Brazil, which is the violence of football supporters, traditionally called hooliganism. In Brazil, especially Pernambuco, imposed two important public interventions about this issue. One was a ban on alcohol intake during official matches, official events, sports events, and the other was a ban on the torcidas organizadas, which is the football firms or football fan bases responsible for most of the violent occurrences in the state. The aim of this work is evaluating these two public interventions by means of autoregressive moving average time series with the inclusion of regressors, the inclusion of exogenous factors, and trying to understand whether these two sanctions were effective or not. My name is Tiago Nepomuceno. I am a professor at the Federal University of Pernambuco. Well, before I start, let me just talk a little bit about this project and its social impact in Brazil. Part of this work was actually published in 2017 in the International Journal of Law, Crime and Justice by me and some of my colleagues from the Federal University of Pernambuco. And since this publication, the papers captivated the interest of civil society and also the interest of some national media, such as Globo Esporte and El País, and the attention from some local newspapers, such as Jornal do Comércio and Folha de Pernambuco. In addition, some legislative councils and justice courts in at least 3 Brazilian states have used this work as a technical and scientific support to abolish or create state laws in 2019. The most recent and valuable contribution of this paper was in 2 judgments on March 6 and March 27 this year by the Brazilian Supreme Court, which is the highest justice instance in Brazil, regarding the direct actions of unconstitutionalities required by governments of the states of Mato Grosso and Paraná, and reported by the Supreme Court's Minister Alexandre de Moraes. Something interesting when we do this kind of analysis is that we are prone to fall in something that we call contradictory dilemmas. Take, for instance, the case of Maria da Penha Law in Brazil. This law, created in 2006 to prevent domestic violence and female homicides in the country, was the object of the study by Garcia and colleagues in 2013. The authors, after analyzing the Brazil using intervention time series before and after the law enforcement, they suggest that there was no significant impact in the reduction of the annual mortality rates, which means that the period before and after the law, they are basically the same. They are very similar. But as pointed out later by Cerqueira and colleagues in 2015, this conclusion was affected by a contradictory dilemma because the similarity in both of the period before and after the law was imposed was due actually to a decrease in about 30% of the female rate between 2000 and 2011, which implies that Maria da Penha law was responsible for preventing thousands of domestic violence in the country and not otherwise. This situation is basically an example of contradictory dilemma because before the law, the country was expecting an increase in the homicide rates. And when the law came, it was sufficient only to keep the rates down to the same level as before, not decreasing any further. That's why some may have the wrong interpretation about the effectiveness of an intervention. Both periods have the same expected value, both periods have the same distributions, but they have the same parameters because the intervention was effective. Otherwise, we would expect a much higher mean in the second period. Building time scenarios can be an interesting methodology to cope with this problem. The time scenario can be defined as an stochastic process created by time observation with the purpose to predict an outcome or a scenario from a past observed reality. In other words, it's how some past observed distribution for a particular event should have been if the intervention did not exist. So the objective here in this work is to investigate how the hooligan occurrences would behave if the interventions on banning the football firms and on banning the alcohol intake were never implemented. Our first results using non-parametric statistical tests, they suggest that there is no significant differences between the time before and after the implementation of the interventions. So when we are building time scenarios and if we observe there is no upward trend in the hooligan distribution, so there is no support for different conclusions than those first results that we had. We model the scenario by considering the effects of time, context, and the exogenous variables. The exogenous variables in our model is the phased public and the importance for each specific match. The phased public is the attendance of a specific match divided by the biggest attendance for that particular club in that particular year. And the importance are related to three categories or three dimensions. The first is competitiveness or derbys, which are the matches with the clubs located at the same city. Supporter pride, which are the matches disputed in commemorative days such as anniversaries or the matches where previous provocations were made by the supporters or by the athletes. And the third dimension is the league position, which is if the match is in a knockout phase or a final or semi-final. We believe that this specific category would impact significantly the number of occurrences if the club wins or loses. The hooligan data corresponds mainly to types of violence, such as assault and battery, contempt, fisticuffs, but also we have some other misdemeanors in the data, such as abuse of authority, slander, lewd acts, among others. About the assessment results, we first wanted to investigate the stationarity property for the process, and we did by analyzing the augmented Dickey-Fowler test results. For both the types of assessments, the alcohol assessment, the football firms, or football gangs assessments, both of them reported a p-value below the significance level, which supports the rejection of the new hypothesis, favoring the alternative hypothesis for stationarity. To define the optimal order for the autoregressive parameter and the moving average parameter, we investigated the autocorrelation function and the partial autocorrelation function. The first cohelogram for the autocorrelation function cuts off at the first leg, and there is no other significant leg after the first one. The cohelogram for the partial autocorrelation function presents a geometric decay. This analysis suggests a moving average of first order should be added to the process. After simulating some model's performance, we have opted for an Argmax 1012, where the first order is for the autoregressive parameter, the second order for the integration, the third order for the moving average parameter, and the final order represents the number of exogenous variables. For the football firms assessment, we have opted for an Argmax 1112. The choice for those models were based in the minimum archaic criterion. The following histograms, they illustrate the application of the parameters in those tables in predicting the past. The first histograms illustrates the distribution of the hooligan occurrences before the law was implemented. And the second histograms on each row, they illustrate the simulation using those parameters, the simulated reality as if the intervention were not implemented. On each case, we have used non-parametric tests for the median and the Kolmogorov-Smirnov goodness of fit for this distribution. The test suggests that we cannot reject the new hypothesis for the equality of median and the equality of distribution, which means that on each case and on each assessment, both the periods before the law and after the law, as if the law was not implemented, they are statistically similar. Well, just summarizing this work, the results suggest that alcohol has not a significant effect or is not a potential determinant for the violent behavior of sports spectators in Pernambuco. When the first paper came out in 2017, some social scientists were invited to comment about the results, and many of them comment that this ban on alcohol was not efficient because it was not strong enough. They allow people to drink outside the stadiums, and because of that, it doesn't make any difference. Well, this is something that goes beyond the scope of this work, but what we can say is that some other intrinsic and contextual factors, they seem to be more promissory in explaining the hooligan behavior, such as matches when they are disputed in anniversaries of the club or in days that mean something for the club. So the hooligan occurrences are much higher, historically speaking, or the league position when the specific match is played for a final or semi-final or hors d'oeuvres. So those factors seems to be more promissory in explaining the hooligan behavior much more than alcohol. About the sanction on banning the football firms or football gangs, it is not that it was a bad policy, it was just poorly implemented. Controlling the interests of the gang members was only made by visualizing the clothes. If the members had nothing that could identify themselves as a member of the gang, of the football gang, so they would not have any much trouble in go in or go out the stadiums. So thank you very much for your attention, and if you have any questions or comment, please do not hesitate in contact me by any of those emails. Thank you.
can hear you.
Yeah, I just realized I was muted. Well, welcome to 2020. Tiago, thank you very much for your presentation. The floor is right now open to the questions. I believe that we have some time.
Yeah, sure.
If not, there is one question for me. Tiago, you've mentioned that the analysis that you have done was for one particular region. However, this method is also spread for other regions in Brazil. My question is, do you found the same results for the other regions, or have you run this analysis for like another samples, let's say, so just applying the same method but for different parts?
Yeah, this is the purpose of our next work that we are currently working on. But for this assessment, we just used the matches in here in Recife. We have this data set from the Tribunal do Torcedor, which is the supporter court, is an implementation from the government here. So they have this the occurrences, the really gun occurrences, those that I comment on the video for this specific region here in Recife. But the interesting part is that for this particular region, we have supporters for all of the country, because we have the clubs that they dispute national leagues, they have international leagues. So we have people from all of the countries, all of the other regions. So we believe that we could generalize those results if we applied this specific assessment on other states as well. But this is one of the purpose that we are currently working on, and so we hope that we can have results also for this assessment.
Perfect. Sounds good. Sounds really good.
Thank you.
Is there another question from the audience? If not, then Tiago, thank you once again for the presentation. And as the next presentation on the agenda is a presentation of mine. So let me share my screen real quick. Sorry. I think that I'm on. Can you confirm that at least?
Yes.
Yeah.
Perfect. Thank you very much. My name is Michał Chujnowski, and I'm the PhD candidate at the last year at Warsaw School of Economics. And today I'm proudly presents the method that I'm investigating, and this method integrates econometrics method with a vast amount of data. Here, for the sake of that research, I will be using Google Trends and trying to figure it out how information from Google Trends can impact the forecasts of the market and also the markets themselves. I'm also like to inform you that this project is financed by the National Science Center of Poland. So firstly, I will introduce what is the environment and what is the scope. So what model we are trying to set up and what kind of answers we are trying to get from it. Then I will make a short introduction showing you the models which are a little bit easier, and it might seem that it's a little bit overcoming to use this method. However, for explaining how this method works and why I'm doing that way, it really helps to start from the bottom here. Then I will explain how I'm integrating the Google Trends and how the Google Trends can be integrated. Then normally there will be results. However, unfortunately, because of my sickness, I had to put on hold the research, and the results as of yet are not, let's say, satisfactory, but I hope that at least I will interest you in the research, and once I get the results, you will lovely to come back to this article. And I'll finish with the conclusions. So the idea is that, especially after the crisis of 2008, where there was the information that actually the rating agencies are a little bit culprit to what has been done, there was more and more literature which investigate how the information flow under the imperfect information actually affects the economy. And the literature has looked closer into the market sentiments, so how the market sentiments can affect both the economy and the market. And it has found out that actually those market sentiments impact the business cycles significantly. To get into more into the details, the market sentiments works as information which skews the perception of the customers. So in this framework, the customers or the firms or the banks face the coordination problem. So because they do not have the perfect information about each other, they are trying to guess what is their best action that they can take. So how many cars, I'm telling cars because the cars is one of the markets that I'm investigating. So for example, how many cars there should be produced, so what kind of targets there should be put on the sales of the cars that are reasonable and effective for the company growth. But also it comes above it. We can also investigate the monetary policies and, for example, check how the impact of the National Bank by changing the interest rate can affect the economy. Mm-hmm. So from the introduction that I've made, you can have the impression that there's a lot of theory, and that's true. There is quite a strong economic background from the theoretical models. However, there's little econometric research which will prove or use this method on the real data in the applied manner. So my motivation for this research and for this paper is that I'm trying to come up with the method and with the framework which includes the setup that these theoretical articles are proposing, and use the real-time data with the applied with the applied setup in mind here. Additionally, because I am also mapping the market sentiments here with the information that we actually can measure outside of the survey-based confidence interval indices, the method also allows to observe in the real time, or at least as soon as the data is coming, what is the market sentiments and what kind of impact can it have on the future market outcomes. As a thematic model that I am the most influenced here, it will be the nonlinear models. So L-star model, which is the logarithmic smooth transition autoregression, and its vector counterpart, the extension more like of the model, which is the vector autoregressive wedge smooth transition. I will also here present the Aremax, as I've mentioned, just to start the conversation and gives you the intuition how this method works. In the literature here, and also here in this method, I assume that there are two regimes, and those two regimes are not, let's say, easily defined by the literature. So I want to keep in mind that the definition of the regimes, it's not that straightforward. What I will be using here is that there is the high regime, which indicates the person who is less risk averse, he's looking forward and eager to invest, and also the low regime, which represents the people which are a little bit scared. They are much more risk averse, and they do not tend to invest or either put a big consumption decisions for the future. And the Google Trends will define the ratio between those two people on the market or in the economy. So what I will have is that, for example, I will have the car market, I will have the car market consumers, and I will trace how many of those customers are actually like to buy the car because they feel that they want a new car, they like to put their money just to treat it as an investment in their life, or the second part of the people which are not eager to risk any money and they are buying a car because they really need to buy a car. So to start with the Aremax part, Aremax consists of the two parts which usually in the literature of hybrid models of ARIMA and artificial neural networks is consists that we have the linear part. So the linear part is the autoregressive part, and so-called the non-linear part. And usually in the literature, the non-linear part corresponds to the random noise that we have, and artificial neural networks are used to explain non-linearity relations in the random noise. Here we assume that there are nonlinear relations in the market sentiment, which in the equation is defined by letter C, I'm sorry. And we're trying to figure it out how Google Trends can affect this market sentiment. So what I really wanted to do with this research is that I wanted to use one optimization process. So I'm trying to minimize the steps of the optimization that we have here. There is a significant literature in ARMA and artificial neural networks, which takes the ARMA first and using the ARMA model, then computes the random noise, and then the random noise is explained by artificial neural network. Here I wanted to use artificial neural network only to represent the same model. So to present how it looks like, for the ARMAs it looks very simple. On the red, I put the linear component of the model. Artificial neural networks allows us to use the linear activation functions. So basically the red part of the neural network is identical to the linear part, so the red part in the ARMA equation. And here I'm not talking about the Google Trends yet. I'm just showing the possibility how the market sentiments can be connected to this model. There's a separate blue branch which is responsible for the sentiment, and then those two parts are added at the end. So long story short, this model, the rest of the architecture that I wanted to show you here, based always on the two basic principles, that there's gonna be some linear model which usually was estimated using the maximum likelihood or the less, and the sentiment part of the model, which will heavily include nonlinear relationships. So let's take this next step and let's discuss the logarithmic smooth transition autograph. So in that part, there is only one variable. So for example, number of car stalls. And there are two kinds of people, optimistic, pessimistic, let's call it that way for simplicity. Additionally to, and each of the people are following different autoregressive model, which can be interpreted as different perception of the past. As an example where this assumption might hold, if you look, if you will examine the person who is more optimistic, then the impact of the lags more into the past might be less important than for the person who is more risk averse and tends to analyze what happened in the past more into the details. So to represent that there is a ratio of those people between those between the optimistic and pessimistic, in the L-star model there is a G function which is called the threshold function, and this function is basically transforming any data that we put, which allows, into the interval from 0 and 1. So usually the threshold function represents the ratio of people which are optimistic, which is considered by G, and there's 1 minus G, which corresponds to the people who are pessimistic. And by arithmetics, we can rewrite the L-star model to the model which you can see in the bottom. So there are 2 autoregressive parts, and only one has the threshold function next to it, which for the artificial network purposes simplifies the calculations much. So this is how the architecture of such the model looks like. Yet again, in the red, I put the linear components here. On the left, we can see the low regime, which have no transition function next to it, and the right red part of the model is the difference between high and low regime. This regime comes from the arithmetics, and there is a multiplication of the market sentiments next to it. That's why the market sentiments are only affecting the difference between high and low here. So once we have it, the vector autoregressive is pretty straightforward. So for autoregression parts, a vector autoregression part, basically the model looks the same, but instead of univariate variable y, we have a vector of the of the variables that we have. And usually the vector autoregressive model is not used that often, both into economic policies and also into market analysis. Is that correlation between those components actually make the computations much more complex than the single univariate variables. There is still a method though, that heuristic one, that if we have the threshold variable exogenous and we allow the grid search, then the estimation from each of the run can be simplified to the model which use the ordinary least square method. But in general, the estimation of this model is not that simple. However, with the auto neural network part, we basically just extend the model that we have from the LST star. So for each of the from each of the regimes, we calculate the values from those autoregressive parts. From the difference between high and low regimes, we take the market sentiment and multiplied those results with it, and then we add it all together. Right now, it seems maybe much a little bit convoluted, but this is basically the just LT star model and copy and paste it by the number of the regimes that we have. So once we have it, then the implementation of the Google Trends is also straightforward, in the sense that here the Google Trends are the time series which Google incorporated, allows us for free to use, and it represents the number of searches of given phrase. And it's normalized from 0 to 100, and 100 represents the maximum value within the range that we have chosen. So how the analysis looks like is that the analysis chooses the names of the searches that he in person finds important for the model. So for the car market, it's going to be the make. It's going to be how much or how many people are actually looking for a loan, for a car loan especially. But also on the other hand, if the people are looking for the unemployment bills and for the possibilities also to sell their goods, it might suggest that those people struggle financially and they will not buy a car. So the base architecture that we have here is we have our base model that I have presented previously, and it is represented here by oval. I just simplify it because there's no need to copy and paste it the same thing. And on top of the market sentiment that we have before, we have created yet another market sentiment, the neural networks part. However, we can also use the other methods here to use our purposes. The angel network architecture that I have named it assumes that there are two nodes before the last node of the market sentiments, and it represents that there are some forces which fights over how the people thinks over the market. So you can imagine that there's like an angel of positive factors and devil on negative factors, which influencing the people's perception of the market. We can also have the predefined groups. So here in previous architecture, I assume that I'm using all the Google Trends that I have. But of course, with more and more Google Trends that I have, the more parameters I have to estimate. So for the Google parts specifically, some kind of Google Trends actually looks very similar. As an example, if I look for a Honda or for a Suzuki, the Google Trends looks very similar. Just because if someone is looking for a car, he's trying to find for a Japanese car. And when he's looking for that, whether it's Honda or Suzuki doesn't really make much more difference. So it is possible to group it. And the question is, well, do we want to cluster it using the artificial networks or by other parts? And one of the things that I am using is actually the Bayesian non-parametric model, which helps to cluster together time series which looks similar. So we can have the predefined aggregation that we wanted to use here. But we can also have the external cluster groups. So I can, as an analyst, decide that those Google Trends are going together, and I'm allowing the artificial network to cluster them together, but not choosing what kind of clusters they are. So as a result, unfortunately, as you can also probably hear from my voice, I had to put this research on hold. However, the results are that the artificial neural networks, although they are promising, they are, because of the increased number of parameters, they still cannot beat in forecasting simple models as autoregressive part, the simple autoregression or the simple L-star model. However, by having this additional neural network, we can have much more information about how the information impacts the market. So for example, which kind of the sources are actually important, or which kind of sources are dominant over one's market sentiments perception, or actually how this market sentiments changes over time. So please forgive me, I do not have any results because none of the results actually will show that this model is beating at least the simple econometric model. Yet, I strongly believe that once I came back fully recovered, I will show you the results, and hopefully I will show you that this method can also bring significant part in the forecasting, at least in the short-term forecasting. So as a conclusion, I want to say this method allows us to really look into how information available affects the market. I am using the Google Trends, but this method does not discriminate other sources, as text analytics of the articles which are publicly available. The Twitter analysis is also possible to do here. Also, the survey-based indices is also possible to use it, as well as other economic indicators. The only part, the drawback that I'm still struggling, is that this method is longer to compute, and there might be less accurate due to the number of parameterization. So there's still a payoff between the information that we have or the time for the forecast. There's part of the literature that I have used for that presentation, and that will summarize my part. Thank you much for your attention. I'm sorry that as the time progresses, probably less and less you can hear of me. However, the floor is open right now for the questions, and I'm really happy to answer if there's any.
Yeah, Michael, just a quick question. Congratulations for your presentation. I have a student that is interested also in working with some market stock prices and including exogenous factors of information. Are similar what you are doing. I just want to ask you if you have the knowledge on how the Google Trends they perform this normalization, because you said in your presentation that it normalizes for a scale between 0 and 100. Do you know how they do that, or you have the? It's just a curiosity.
So I mean, it depends also I believe I have to check it, but I believe that it depends on the period that you're taking. So once you're using the Google Trends, you can also choose the period, which starts from January 2004. And for example, if you choose the other period, the Google will normalize the 100 to that period that you have chosen.
It's very similar to the Google Mobility Report. I think they do the same time. It shows a period and yeah. Okay. Okay, thank you.
Also, the frequency of the Google Trends is different in the sense that if you take the 5 years and longer, you will receive the monthly data. But if you took, for example, 3 years, you can have the weekly data. And if you take the last 90 days, you can have the daily data. So also for example, for the financial forecasting, my method is also applicable and can be also used implementing these Google Trends.
Yeah. This is interesting because it changes the interpretation of the parameters when you're estimating the normalization also process. So you can have a different interpretation depending on how the data were normalized. Yeah.
That's true. Unfortunately, I have to cut the discussion because we are just running a little bit under time. If there's any other questions, please reach out to me. I am really happy to answer those and discuss the model with you. And right now, I am happy to present the last presentation for today's session. It's the presentation on Moniac. And please give me yet another 10 seconds to set the things up, and I'll come back to you really in a moment. Right. Please tell me if you see and hear.
Right, hello.
Yes,
Good morning, everybody. I hope you're all safe and sound. At the outset, I would like to thank ISF's organizing body, especially Tao and Pam, for arranging everything, despite all the virus and despite all the chaos. I am Moinag Bhaduri, an assistant professor at Bentley University in Massachusetts, and in just a little while, I'm going to describe to you a way in which you can generate forecasts out of a temporal pattern when you know for sure there could be structural breaks present. So normally I work on change detection problems in a continuous time point process, and today I'm going to describe to you a very crucial subclass of it, the self-exciting subclass, where one event triggers or untriggers several others in a very close neighborhood. Several phenomena, several natural and artificial phenomena fit this framework, this context. Very often we find, for instance, a major earthquake followed by several minor aftershocks. Terrorism or gang violence could be another example where one attack as if causes several retaliations over the next few days. Through this work, we are trying to check whether changes have happened both in the way the major and the minor events emerge as time goes on. I need to quickly take you back to the way these stories are normally modeled. I recall we usually assume there is a mathematically nice function called the intensity function, shown here through lambda, that controls the instantaneous probability of observing at least one shock over a very small period of time. Now, specifying the intensity function is not enough to describe the system entirely. you must also know something about the underlying probability law or the distribution. So if that law happens to be Pearsall, meaning if the probability of observing a given number of shocks by a given time period is expressed according to that Pearsall expression, then the sequence is a Pearsall process, and this is how the intensity enters the system as the rate of a Pearsall variable. So the underlying Pearsall distribution and the intensity teaming together, they drive the entire mechanism. Through this work, we are trying to question the nature of this underlying intensity, especially whether it's a constant function, independent of time. Graphically, that would lead to this kind of a monotonic flow of shocks, a stable or a stationary system, that is. Intervals of the same length are likely to contain the same number of shocks, regardless of where you are on the time axis. If, on the other hand, your intensity increases, then as time goes on, you'd expect more and more shocks, and your process will be deteriorating. As our alternate choice of the underlying intensity, we felt that this expression, shown here through equation 1, does a very good job in describing the self-exciting property with the blue piece. The first portion describes how your major events happen, and your green function, the second piece, describes how your minor events emerge as time goes on. You'll find that this is a data-dependent intensity. The y values here, they represent the times at which these events actually took place. And depending on your choice of the green memory kernel, you'll have different interpretations of this forgetting the past property. One very common choice of the memory kernel is the exponential kernel, where a high value for beta will tell you that you're forgetting the past very, very fast. Your memory decays very, very rapidly, while a low value of beta will tell you you have a long memory. Now, how much history is relevant to your problem is controlled by this window of size R. And here we have worked with the most general case of an infinite history that leads to a Hawkes process. Now, this often leads to a branching process structure where observations coming out of the blue portion are equivalent to the first generation events, or the immigrants, and those coming out of the green portion of the second generation shocks, or the offsprings of these immigrants. Through this work, we're trying to check whether changes have happened in either or in both colors as time goes on. In the context of the gang violence example, for instance, the change in the blue piece could be because of something external or exogenous to the system. Maybe some kind of a political regime switch, or the appointment of a new police sheriff in town. And a change in the green portion, it could be because of something internal or endogenous to the system. Maybe you lost the desire to seek revenge because of an attack, which might not have anything at all to do with the appointment of a new police sheriff. So here's one quick simulation graphic that describes what kind of intensities will lead to what kind of data. To your left, you have a data-independent deterministic intensity, something that you can write out prior to observing your data set. And a spike in that kind of an intensity leads to a clear crowding, a clear clustering that is easily visible, in this case to your right. Whereas on this panel, the one to your right, you have a data-dependent, random self-exciting intensity, which goes up every time you have a new shock coming in. The first generation change it was placed here at 50, and the second generation change was placed at 75. And I'm sure you'd agree that the crowding, the clustering is not as vivid, is not as clear as the one to your left, which undoubtedly leads to a harder, more complicated detection exercise. Conditional on the change point, the observations to your left, they are independent of each other, while the ones to your right, they're dependent on each other. So through this work, we're trying to look at the data, the top panel that is, and we're trying to pinpoint locations at which the bottom panel goes through some kind of a significant change, presuming there is a change at all. And one way to do just that, one way to check whether you have a significant change is through this statistic called the forward function, the forward statistic, which is extremely well known in the literature. It's known to lead to a few optimal tests, and it's defined through log combinations of the time ratios. Another modification to it is when you keep the same structure, but you simply switch the time ratios about 1. So Z and ZB, they're very opposites of each other, and because of the way log functions work, it isn't hard to show that a deteriorating sequence will inflate the value for ZB and will deflate the value for Z. And in more recent times, we have worked with the maximums and the minimums of these two variations to check whether we can detect changes under a deterministic system. We found them to have quite good classification power, and we are now trying to find whether some of that power will translate to a harder scenario of self-exciting intensities. And here is an answer to that very question. Basically, a 3D power study where along the wall you have the probability of correctly classifying a self-exciting process as a self-exciting process, and along the floor you have the pre and the post change beta parameters. You would notice that when these are very, very similar to each other, the pre and the post change parameters are very, very similar to each other, along the diagonal that is, detection is understandably very, very hard, very complex, which is why you have a valley in these power mountains and along the diagonal. And when they're very, very different from each other, along the corners, along the edges, detection is relatively simpler. So these mountains are very, very steep in those regions. So the green surface is the left base test, I guess, yes. And the blue is the R-based maximum test. And you would notice that there is no clear uniform winner. There is an asymmetry in these power mountains about this diagonal. Now, this power exercise, it helps you check whether you have a change at all. It doesn't help you locate it. It doesn't help you find the precise location. So to do just that, our proposal is to do a sequence of tests, a sequence of hypothesis tests with the 4 statistics that you just saw. And essentially, we are claiming that if there is a test that sits in the first set of 16 observations that says things are fine, and if there is a neighboring test on the first set of 17 observations, one more, that says things are not fine, then the change must have happened somewhere in between the 16th and the 17th observation. So there are a few technical details you have to be careful about because you are doing a sequence of tests. Your false discovery rate will have to be controlled. The problem with the null set, what happens if you do not find a change at all? But barring those, this is the overall idea. So we tried to check whether this algorithm was any good through 3 real examples. And for each one of these, we did some goodness of fit tests prior to all this to check whether the self-exciting assumption is at all valid. So the first example is from finance, where we have a web page that stores data on economic announcements that are likely to cause different types of impacts on the financial market. It's quite a large data set, and we have focused on 3 different types of announcements: the high, the medium, and the low importance announcements. Categories only on the United States. So if you apply our change detection algorithm with these 4 different types of statistics that you saw, your answers will be these vertical strips, these separators. So the message from this analysis is the number of change points we find our way doesn't have to be bounded. It correlates very often with the size of your data set. The more data you have, the more prone you are to having several of these separations. This is quite unlike some of the techniques we currently have. Another example I looked at was the global terrorism data, which is again quite big, which is why I've sampled 3 violence categories. The estimated change points here are more visually acceptable. Our best guesses are times when we have sharp bends and edges. Historically, these are acceptable too. These separations, for instance, they represent the 1970s when bombing was quite common in the United States. Change points from these armed assaults are placed in the more recent past, signaling deterioration, which again makes intuitive sense. Now, in both these examples, you found that the answers shown by these 4 different tools through these 4 different colors are thoroughly mixed up. That is not a guarantee, though. We might have a few other examples, like our tsunami example, where colors might be separated by a constant amount, where the blue might lag the red by a predictable amount, almost always. Now, this begs the question, which tool to trust when? And to answer it, and also to check how this proposal stacks up against some of the competitors we already have, we will move on to the last section where we will recollect a few ways in which you can do change point analysis without using the sequential approach. The general problem of change detection has been attacked from several fields, especially since the 1950s. The one construction that proves extremely useful was introduced by Hawkins and others, where with a given sample size, they have translated the entire problem into finding several of these two-sample statistics, these DKNs, measuring the distance between the pre and the post-change pieces for a fixed initial guess at K. The best guess that is of the true change will be that K that maximizes some overall profit function, or that minimizes some overall loss function. Now, there are different choices of these two sample statistics. In the interest of time, I won't go into details, but I will indeed point you to a beautifully written review article by Trung and others, where every choice is elaborated along with the logic behind it. The first test we wanted to run was this average run length test under the assumption of stationarity, under the null assumption. This is essentially based on the idea that if you do not have a change at all, then your estimate should be at the end of the time sequence. We found this to be true for most of our proposals via L, Z, R, and ZB. And even for our competitors, we have implemented two types of simulations. Now, the first type was failure truncation, when we're waiting for 400 shocks, 400 events, no matter how long it takes to reach that far. And the other is time truncation, when we are waiting for 400 units of time, no matter how many shocks we receive by then. Moving on to slightly less trivial examples, we examine changes in the first, we examine changes in the second generation events initially, your green function, that is. So on these diagrams, we're assuming that your first intensity, the blue piece that you saw, is constant at 1. And the only change from a 3.8 to an 0.8 beta-wise, which is a deterioration, by the way, happened at time point 100, shown here through this dashed line, which is the point in time around which we would expect the tightest clustering. The first thing that struck me was quite a few of these competitors are generating quite a few, lots and lots, in fact, of change points, some of which are even prior to the actual change, which are definitely false alarms. We are doing better in that regard. Most of our proposals show crowding after the true change point really happened, which is always a good sign. Moving on to the slightly more complex example of two changes. Here, the change in your blue function, your baseline intensity, will change from 1 to 2. That happened at time point 50, shown here by the heavy broken line. And the change in your green function, which is again a very similar change, happened at time point 75, shown here through the fainter dashed line. Again, you would find that most of our competitors are signaling too many false alarms. And most of our proposals, especially on that side, on the time truncated side, we are Z, ZB, R, and L. They demonstrate the clearest, the strongest right-skewed clustering after those two very points. Points like this and points like those, for instance. So both those examples, they were done with a fixed sample size in mind. A natural worry is what happens if I have a progressively increasing sample size, very similar to the terrorism example or the finance example. Now, these graphs, they help you resolve that problem somewhat. And here we are not so much worried about the location of these changes. We are more worried about the actual number of detected changes. K is the actual number of change points. For the simulation study we set K to 2, and I was trying to check whether the probability of detecting the right number of changes approaches 1 asymptotically. We found that for most of our competitors, that long-run probability decay is very, very fast, very, very rapidly, while for most of our proposals, although we are not reaching 1 all that fast, we are not dropping either. So this demonstrates that if you stick with our proposal, then if you wait sufficiently long either in terms of data or in terms of actual clock time, you will ultimately weed out the right number of changes. You will ultimately pick the right number of change points. You won't overcount or you won't undercount. Now, once you figure out the change point locations, you can measure the distance between two countries' financial announcements through Hausdorff type proximity measures. The heat map to your right, for instance, shows that according to that metric, Indonesia's announcements, they closely mimic the United States, since predominantly we have cold patches. Or you could cluster a bunch of countries. You can put countries with similar change point structure on a specific branch of a cluster tree. In recent times, there have been lots of papers like the one you see here, where it is described how separate models on separate regimes can improve forecasting power through tinier forecast intervals and better accuracy metrics. The change point work that you've just witnessed helps to answer the first question reliably, the regime definitions, so subsequent questions can be more tractable. So that's really all I had for you today. We found how a small change in the way time normally flows from the left to the right to the right to the left, meaning a change from Z to ZB, can trigger lots of useful statistics like the minimum of those two, like the maximum of those two, and in turn a fresh algorithm based on multiple testing that can help you detect changes in the self-exciting property without sounding too many false alarms. This approach is quite distribution free. Never did we assume we have to have conditions like the at most one change point condition, which quite a few techniques currently do. Because for us, as soon as we find out one change point, we can restart the algorithm to find out the next. It's not extremely computationally heavy, it's quite fast. If you figure out these changes, then you can impose whatever favorite inter-event distribution you have in mind to forecast future observations too. Some references. The first describes the change detection algorithm in greater details, and these two would be the review articles that I talked about. Thanks for listening. I'm always interested in meaningful collaborations, so if these sound even remotely relevant to what you do, please let me know. But more crucially, stay away from the virus, stay safe, have a wonderful conference. Bye-bye.
Yep. I'm ready to answer questions, if any at all.
I see no question from the audience. I have to cut the presentation right now. We ran a little bit out of time, which I apologize for that. Nonetheless, presenters, thank you very much for your presentations and for sharing with us your research. It was very inspiring, interesting. Glad that I attended and chaired this session. And also I'm happy to the audience that they have joined our session. Please do enjoy the rest of the ISF and hopefully see each other on the other Zoom meeting.
Thank you. Thank you for chairing.
Bye-bye.
Thank you, everyone. Bye-bye.